Good morning, everybody. My name is Gaurav Chaudhary. I'm assistant professor in IT department in Ajay Kumar Garg Engineering College, Ghaziabad. Today, I will be discussing the topic of Hadoop, in which I will be discussing the components, the building blocks, and finally, I will be discussing the MapReduce model. So, what is Hadoop? So, formally speaking, Hadoop is an open source framework for writing and running distributed applications that process large amounts of data parallelly. So, in this, the processing is happening in a distributed fashion as well as in parallel fashion in the nodes of the cluster. So, now coming to the components of Apache Hadoop. The Apache Hadoop framework is composed of basically 4 components. First is your Hadoop Common, which contains the common libraries and utilities needed by other Hadoop modules. And then we have got the SDFS, which stands for your Hadoop Distributed File System, which is a distributed file system that stores data on commodity machines, providing high aggregate bandwidth and throughput across the cluster. So, across the nodes of the cluster. And then we have got Hadoop Yarn, which is a platform responsible for managing computing resources and clusters and using them for scheduling users' applications. And the last 4th component is your Hadoop MapReduce, which is an implementation of MapReduce programming model, which is a parallel programming model for developing MapReduce jobs. Now coming to the building blocks of Hadoop. So by building blocks of Hadoop, we mean is what it means to run Hadoop framework on a commodity machine or a cluster of nodes. So the building blocks of Hadoop are basically your background processes, which are the daemon processes, which runs on the various server. Either they run on a single server or they can run across several servers. So the daemons include your name node, data node, secondary name node, job tracker and task tracker. So these are the 5 daemons which are required to run Hadoop, and these are the building blocks of Hadoop. Now Hadoop employs a master-slave architecture for both distributed storage as well as distributed computation. So because the processing of data is happening in a distributed fashion as well as in parallel fashion, so for storing purposes and also for the computation purposes, the architecture which is employed by Hadoop, it is the master-slave architecture. And we have already seen that the distributed storage system is called the Hadoop file system or the SDFS, which stands for Hadoop Distributed File System. Now coming to the first daemon, which is the name node. So your name node is the master daemon of SDFS that directs slave data node daemons to perform low-level I/O tasks. The function of name node is memory and I/O intensive. So as such, the server hosting the name node typically does not store any user data or perform any computations for a MapReduce program to lower the workload on the machine. This means that the name node server does not double as a data node or a task tracker. So because it is memory and I/O intensive, so it will not double as a storage, or it will not double as a computing intensive operation. So there is, there is unfortunately a negative aspect to the importance of name node, which is a single point of failure for your Hadoop cluster. So this is a negative aspect, though it is memory and IO intensive and it does not double as a data node or a task tracker. So it becomes a single point of failure of your Hadoop cluster, being the master of SDFS. Now this next daemon is your data node. When you want to read or write a HDFS file, the file is broken into blocks and the name node will tell your client which data node each block resides in. So your data nodes, they are constantly reporting to name node, and upon initialization each of the data nodes informs the name node of the block it's currently storing. Next, coming to the secondary name node daemon. So your secondary name node daemon, this is an assistant daemon for monitoring the state of the cluster SDFS. So it is on the top of your name node server. So all these daemons, as we have already said, that all these daemons, they either they are running on the single server or they are running across several servers at the same time. So your secondary name node is an assistant daemon for monitoring the state of cluster SDFS. Like the name node, each cluster has one SNN. So every name node has an SNN because SNN is on the top of name node, and it is an assistant daemon for monitoring the state of name node. And it typically resides on its own machine as well. So it is a separate server than the name node server. As mentioned earlier, the name node is a single point of failure for a Hadoop cluster, and the SNN snapshots help minimize the downtime and loss of data. Nevertheless, a name node failure requires human intervention to reconfigure the cluster to use this SNN as the primary name node. So when there is a failure, then it minimizes the downtime and loss of data. But if you want to make the secondary name node as the name node, then it will require a human intervention. It will not be automatic, though it will help you in minimizing the downtime and loss of data automatically. The next daemon in the Hadoop framework is your job tracker. So the job tracker is the daemon is the liaison between your application and Hadoop. Once you submit your code to your cluster, the job tracker determines the execution plan by determining which files to process, assigns nodes to different tasks, and monitors tasks as they are running. Should a task fail, the job tracker will automatically assign the task, possibly on a different node, up to a predefined limit of retries. So like the name node, there is only one job tracker daemon per Hadoop cluster, and it's typically run on its own server as the master node of the cluster. So your name node and data node, they work in the master slave configuration, whereas your job tracker and the task tracker daemon, which we are going to see the next, they also work in the master slave architecture. So coming to task tracker, as with the storage daemons, this is the computing daemon. So your data node, that was the storage daemon. Now this is the computing daemon. Also follows the master slave architecture. The job tracker is the master overseeing the overall execution of MapReduce job, and the task trackers manage the execution of individual tasks on each slave node. So you can see this figure where the job tracker is in the master configuration, whereas the task trackers, they are in the slave, they are the worker nodes, and they are the it is in the slave configuration. So each task tracker is having a map reduce job to work upon. So each task tracker is responsible for executing the individual tasks that the job tracker assigns. Although there is a single task tracker per slave node, each task tracker can spawn multiple JVMs to handle many map or reduce tasks in parallel. So instead of having a single task in a task tracker, you can have multiple tasks also by spawning multiple JVMs. One responsibility of the task tracker is to constantly communicate with the job tracker. If the job tracker fails to receive a heartbeat from the task tracker within a specified amount of time, it will assume that the task tracker has crashed and will resubmit the corresponding task to another task tracker. So this is the typical topology of a Hadoop cluster, total topology. So like I said, the secondary name node sits on the top of your name node server. Your name node server has its own server and also your secondary name node has its own server. But your job tracker can reside in the same server as the name node server. Job tracker can reside in a different server also, depending on upon the requirements. But in this topology, the typical topology, we have the job tracker residing in the same server as the name node server. And then we have the connections to the cluster nodes, which are servers or the commodity machines. And there we can have data node daemon as well as task tracker daemon on the same server. So your name node and the data node, they are the storage daemons. They work for the storage requirements, and they work in the master slave configuration, whereas your job tracker and task tracker, they work for the computing part, and they also work in the master slave configuration. Now we saw the four components of your Hadoop framework. So having seen the building blocks of Hadoop framework, I will like to talk about the map reduce programming model or the processing model. So the map reduce is a data processing model. Its greatest advantage is the easy scaling of data processing over multiple computing nodes. Under the map reduce model, the data processing primitives are called as mappers and reducers. So decomposing a data processing application into mappers and reducers is sometimes non-trivial. But once you write an application in MapReduce form, scaling the application to run over hundreds, thousands, or even tens of thousands of machines in a cluster is merely a configuration change. This simple scalability is what has attracted many programmers to the MapReduce model. So basically the mapper is meant to filter and transform the input into something which the reducer can aggregate upon. So this is how you break the large data into smaller parts and assign it to the mapper functions, and then the reducer will aggregate over the outputs of the mapper functions. So this is the functional model of your MapReduce programming model. Here we can see the input and output of the MapReduce operations. So in between your MapReduce operations, in between the MapReduce operations, you can see the combine, shuffle and sort, which are the intermediate steps which are performed between the map and reduce operations. So your combine is also called as your local reduce operation. So it may be used, it may not be used. So these are your intermediate steps which are there, and the output of this intermediate steps is followed after the map function output, and the resultant output is fed into the reducer function to get the reducer output. So in your, we can see that in the input map we have got key value pairs, and the output of the map function is your list, which is again your list of key value pairs, and the input to the reduce function is a pair of key values and a list of values corresponding to the keys, corresponding to the same key, and then we get a list of key value pairs as the output of the reduce function. So in map, if we see on the right side, the map function is, it transforms key value pairs into a list of key value pairs. So the input to your application must be structured as a list of key value pairs, and the list of key value pairs is broken up, and each individual key value pair is processed by calling the map function of the mapper. In practice, the key K1 is often ignored by the mapper. The mapper transforms each K1 V1 pair into a list of K2 V2 pairs. For example, in the output list, we can have a pair foo1, which is a key value pair, 3 times from 3 different documents. We can have a pair foo1 3 times. Now, after we get the map output, the intermediate steps are performed, which are the combine and sorting operations, which inherently involve the shuffle operations. The reducer input is a pair of keys and a list of values corresponding to the same key, and then we get a output as a list of key value pairs. So all pairs sharing the same K2 are grouped together into a new key value pair, which is K2 comma list V2, and the framer asks the reducer to process each one of these aggregated key value pairs individually. The map reduce framer automatically collects all the K3 with V3 pairs and writes them to file. Now in the following word counting example, the map output for one document may be a list with pair foo comma 1 3 times, and map output for another document may be a list with pair foo comma 1 twice. So this is a key value group. So conceptually, the aggregated pair that the reducer will see is a pair of key and a list of values, which will be foo comma list of 5 ones. So in word counting, the output of our reducer will be foo comma 5, which is the total number of times foo has occurred in the key value pairs. So if we see the map reduce word counting example flow, so we can see the map column, which is the map function output. So and after the map function output, the combine and shuffle and sort, these are the intermediate steps which follow the map function output to make the resultant map function output, and your resultant output is fed into the reducer, and what we are seeing under the reduce column is the reduce output. So, under every column, so under map column, we are seeing the output of the map function. Under reduce column, we are seeing the output of the reduce function. So, if we see, for example, here in under the shuffle and sort column, if we see your SQL comma 2 and SQL comma 1, SQL comma 1, SQL comma 1, all these values are coming from 4 different documents. So, what the reducer will see conceptually, it will see SQL comma 5 ones, and your that will be aggregated by the reduce as SQL comma 5, which will be the reduce output, and which will be finally collected in a file in the output function. So, and also we can see here is what we can see here is your combine operations. For example, your SQL comma 2 is a combine operation which is there in the first block, which is under the map column. So, we are seeing a local reduce operation, which is also called as the combine operation. So, this is how your map reduce word count example flow happens, and this is how your map reduce model works. Thank you.